Hi, this is Yvonne Santiago, and I'm going to review some concepts from the Hydrology for Hydraulics course. We have talked about the hydrologic cycle. Make sure you watch those YouTube videos that I have included in the slides. And what's important is that we have the hyetograph, which is the actual storm that shows the intensity with time for the storm. And then there's the watershed response to that storm, which is the hydrograph. And the hydrograph has a shape similar to this, where you will have your maximum volume and your maximum flow rate, the peak. We can use either one, whether you use the volume or the maximum peak for your calculations. And remember that the volume would be the depth of the storm times the area of the watershed. So um, really we can use this maximum depth of the storm or Qmax. Okay, so for our design we can use either one. So summarizing, the hyetograph is the rainstorm. Depending on the basin characteristics is the hydrograph. The basin characteristics would be issues or features such as the basin size, topography, the length of the streams per the area, or drainage dentistry, vegetation type and distributions, geology, soil type and thickness, and of course the runoff processes. This is an example of an actual hyetograph with a rainfall event and the response hydrograph due to that rainfall event. Remember then the hydrograph, the response to that storm, will have a rising limb, a Q peak. We have the recorded discharge, which is that volume, the direct runoff, and you have the estimated base flow. So you have the recession past that peak. One thing that's important is that you have the duration of the storm and you have an excess precipitation and a time to peak, and then a time of concentration, which is from the farthest point from the storm, from the beginning of runoff to the time at which the entire watershed is contributing runoff. Okay? Um, that's how we design, for example, uh, storage basins or reservoirs. So, retention or detention basins, um, where you have a normal water elevation, so you have to calculate that volume that has to be stored in that basin. We talked about the difference between a detention pond and a retention pond. The detention pond is a dry pond, very similar to what is built in subdivisions. And then the retention ponds, which are the wet ponds, um, which generally retain some volume of water. You have structures like dams, and then you have an outlet pipe that it's um, above a certain level. But then again, here in the desert, sometimes you don't have any volume because it evaporates. But if you see this outlet entrance, then you know it's not a detention but a retention pond. Sometimes we combine both, and also we have what we called bio detention ponds, which is including vegetation and plants, uh, like we have at the Centennial Plaza. So let's say we don't have a stream flow gauge. How do you calculate that excess runoff? Well, there's two methods, the curve number method and the rational method. With the curve number is a parameter that indicates how much runoff is generated from a storm, and it goes from 0 to 100, and it depends on different features like antecedent moisture condition of the soil, hydrologic soil group, soil cover type, and percentage of impervious areas. So what you see here is the antecedent moisture condition would be telling you which hydrologic soil group it belongs to. You have the antecedent moisture condition 1, 2, and 3, and hydrologic group A, B, C, or D. And then once you have your hydrologic soil group and antecedent moisture conditions, you will look for the cover type and the hydrologic condition with this table. These are other examples of curve numbers. And so once you have selected the curve number, you calculate the cumulative runoff in inches, R, um, by calculating um, the curve number, right? So you have the curve number, you calculate S, which is the soil moisture storage deficit in inches at the time of the rainfall. And so this P here, it depends on the storm selected. And so you calculate the curve number. From the curve number and your P, you calculate then your S. And R is that cumulative runoff or rainfall excess in inches. So you can do it with the equations here, but this here shows how to solve it graphically whenever the intensity equals 20% of that storage capacity, which is a commonly used factor. In class, we mentioned the runoff example, and we discussed it, so I'm not going to go over that now. We used these conditions. Be sure to stop and look at the example. Here is the additional example where you have a combination of soil types and different areas. Remember that the curve number value that you used is a weighted average. So you look at each one of the curve numbers that you had and make sure that you have the weighted average. Make sure you pause the video and understand this fully. Okay? So I have included in Blackboard some examples for El Paso of how the curve numbers were estimated for different areas of the city. You can find that in the El Paso County Stormwater Master Plan, which is in Blackboard. So let's talk about the time of concentration, because it's an important feature needed for the rational method, but also to understand what's happening in the watersheds. So the time of concentration is the time from the beginning of runoff to the time at which the entire watershed is contributing runoff that reaches the watershed outlet. Okay, it's also called the travel time from the hydraulically most remote point in a watershed to the outlet. We saw this already, so this time of concentration is very important. The maximum QP occurs when the duration of the storm equals the time of concentration. So the duration of the storm depends on many factors, but if you have a duration of the time of the storm, TR equals to time of concentration, that's when you have your max QP possible for that storm. There are ways to calculate or estimate the time of concentration if you do not have a hydrograph, and look at these equations in your textbook. You have to add sheet flow, shallow concentrated flow, and open channel flow, and the time of concentration would be the summation of those. These are just plug and play equations. But the alternative procedure that we use most commonly to calculate the time of concentration is this, where you will need your curve number here to calculate your soil moisture storage deficit, and then with that S you have here, the time of concentration can be calculated. Remember, the units are important. This would be the time of concentration in hours, and then the length of the longest flow path in the watershed in feet, and Y is the average slope expressed in percentage, not decimal but percentage. So if I say 8%, it's the 8, or 10% is the 10. But if I say zero point 0.1, it's not uh, it's not zero point 0.1. Okay, uh, it has to be in percentage, so it would be that 10%. So we're going to calculate the peak flows for designing hydraulic structures. If you remember, whenever we were using the curve number, we end up with the depth of the storm, and that multiplied times the area gives us the maximum volume. Now we're going to calculate the maximum peak. Remember, we can do either one for our design of hydraulic structures. Uh, so the rational method is the oldest and most widely used to size hydraulic structures. Whenever it refers to drainage inlets, storm sewers, drainage channels, and culverts. So the rational method, this is the equation Q equals CIA, where C is the coefficient of runoff, similar to the curve number, but I here is the rainfall intensity. And remember, for if you are not designing and you just want to calculate the peak flow for a storm, you have to then look for a duration of a storm and calculate the intensity. But if it's for design purposes, what we do is we set the duration of the storm equal to the time of concentration, and then the area is in acres. So in summary, the procedure to calculate that peak flow is: what storm are you designing for? 10-year, 20-year, what is the location? So that then that gives you the information to find the intensity, depth, frequency curve or table from that location. So from this information you find that intensity. Then you calculate the TC, and then the time of concentration. Assume that duration of the storm equals the time of concentration. Calculate C, and then of course this is CIA, so you need that area as well. So let's go one by one. What design storm are you going to use? Well, it depends on the hydraulic structure. If it's a 50-year storm for like culverts and bridges, these are hydraulic structures. This is according to TxDOT. Okay, so you need to check if it's not TxDOT property or highway. You need to look at the city design features, and we'll look at that. So you look at the El Paso drainage design manual to then determine the flow rate for each watershed. If you're going to design retention or detention basins and inlets and other drainage structures within the city, okay, not TxDOT. If it's TxDOT, you look for TxDOT, okay? So we mentioned the bioretention ponds earlier, and the bioretention ponds, the city has guidelines for that, and this is taken verbatim from the city manual. You have some design standards, so make sure you have that. This is for detention basin design, so sometimes they'll give you the storm rather than you having to go and calculate the intensity, depth, the frequency. They already give you what is the depth of the rainstorm that you need to design it for, and then just calculate the runoff in acre feet, the volume, with this equation. That includes conversion factors. So this is just for your information of some of the requirements. Then the second step was to look for the intensity, duration, frequency, and of course depends on the location. This is one curve, generic curve that you use for the examples. But if you look at depth, duration, frequency for Texas, there's a USGS handout that was developed in cooperation with TxDOT. You have that in your blackboard as well. And this is the precipitation intensity duration for 100-year storm. In El Paso, you have here El Paso, so you have the duration of the storm, and you go here, and then you find the intensity. This manual also gives you the parameters to draw yourself these curves for the different storms. But then also there's some figures of the different depths of the storms in case you want to use the depth instead of the intensity. Also, specifically for El Paso County, FEMA developed other depth, duration, frequency tables that you will find. This is taken verbatim from that. But also I found this really neat Excel file that gives you the rainfall intensity duration for different El Paso counties. This was prepared by TxDOT as well. So you just look for the El Paso County and then you get the 2, 5, 10, 25, 50, and 100-year intensity. So you're not getting the depth here, but the intensity. Okay, so here in this Excel page, you just change the time of the concentration, which you would use for your duration of the storm for design purposes, and then you have here the intensity in millimeters per hour or in inches per hour. So how do you determine the time of concentration? Remember, we use these equations. Then the runoff coefficient. What coefficient do you use? Well, you have to use your judgment as an engineer. There's a range. So the peak flow would be CIA. So the larger that C coefficient, the larger the peak flow. So you have to have a larger hydraulic structure, so it'll be more expensive. So you have to, as an engineer, look for ways to find an appropriate number that won't increase the price significantly. Okay? But whenever we look at pre and post construction runoff coefficients, you need to remember, for example, in this case, croplands, if you have 0.25 to 0.35, and then you say, okay, now I'm going to have a parking lot, or let's say an apartment complex, then you need to make sure that the pre, you have less runoff than the post. In the post will generate more, and that has to be reflected by the coefficient that you choose. Okay, so let's look at this example, and I think it's important to discuss this more thoroughly. So the 10-year peak discharge, you need to estimate before and after development for a 250-acre watershed whose predominant land uses horse pasture, and it's a clay loam mixture with an average land slope of 8%. The land use is scheduled to change over the next 10 years to single-family residential with half-acre lots. We'll assume an IDF. Remember, IDF is intensity, depth, frequency. That was provided, and the hydraulic length for that watershed is 4,500 feet. So these are the steps. What storms are you designing for? For example, 10-year. In this case, the example gives you it's a 10-year. What is the location? And to find the intensity, well, I already told you we were going to use that figure that was provided, which is this one. So I'm not telling you the location, but I'm giving you the IDF curve. If I don't give you the IDF curve, then you have to find it for the location, specific location that you're looking for. And then, So we have this, and you have to calculate TC using these equations. Um, so a few things for those equations. Remember that since we're looking at the curve number, even though this is the rational method, we're using a curve number anyways. So you have to look uh, for design. We commonly use B, but if we went to C, would be a little more conservative. Um, and for example, uh, if you have clay soils, then you would go for hydrologic type D. So it would be this um, entities and moisture and D, the most conservative of all. But if you have some loam, then you need to maybe do C. Um, so in this example, and I'm going to look for the C soil groups, and we had the pre-construction is the pasture grassland, and the post was the half-acre lots. And we'll also look at how it changes with the soil group D. But what we have here is that the curve number for pre is 74 and post is 80. So when I look at these equations with 74, let me just write it down real quick. So I have the S equals 1,000 minus 10, 74 over 74. So my S here is 3.51, and then my time of concentration, the length is 4,500. So this is 2.8, as that is 3.51 plus 1 to the 0.7, 1,140, and the slope is 8%, so I put the 8 here to the 0.25. And these are my times of concentrations in hours, and then I convert it to minutes. So if I had soil group D, so this is for hydrologic soil group C, and this is soil group D. Okay, so you can practice with both, but of course for the exam it would be clear. So I look at the pre-development, and the time of concentration for pre-development is 45 minutes, and for post is 37.4. So here is the 45 minutes, and here is the 37.5 minutes. So you have here an intensity of 3.1 more or less inches per hour, and here we have 2.8 inches per hour. Now this is really important, because what we see here is that a storm with a duration of 37.5 minutes would have an intensity of 3.1 inches per hour. And a storm of 45 minutes would have an intensity of 2.8. So what we see here is very normal, where we have the shorter duration storms are more intense than the longer duration storms. So you have a 37.5 versus a 45, and the intensity for this is higher, 3.1 inches versus 2.8. Okay, and that's what we'll see. As you increase duration, the intensity is lowered, and that's the shape of that graph. Okay, so you can see something that maybe you have intuitively recognized or seen in our storms, so that when it rains for a long time, it's less intense. When it rains for a short time, it's more intense, generally, right? So let's take a look at the pre and post. So what we have is Here we have the clay and loam, that mixture. So the clay, of course, is more impermeable than the loam. So we'd have a coefficient of runoff between those numbers, and the post is zero point 0.3 to zero point 0.5. So this is what I was telling you as before, that as an engineer you have to make sure to think of the pre and post development uh, effects. So if you have pre and you have agricultural land, you should have less runoff than if you have residential, because you have more concrete. So here is the range is zero point 0.3 to zero point 0.5, and here is 0.35 to 0.45 and 0.45 to 0.55. So would you use a 0.55 for pre and a zero point 0.5 for post? No, because you need to make sure that the pre and post reflects the reality of the situation. So I can say in a conservative way, okay, I'll use the 0.35 for my agricultural land. Remember that the equation is Q equals CIA. The larger the C, the larger the runoff. Okay? So, and then use zero point 0.5 for my post, for example. And think about this and pause this video if necessary to understand this. That I would not use 0.55 as my factor for pre and then zero point 0.5 for my post, because what I would be saying there is that there's more runoff in agricultural land than in residential land, and that doesn't make sense. Okay? So I have my Q equals CIA, and then let's take a look at the units. So QP would be in acre inches per hour, and the C is the runoff coefficient, which is dimensionless, and then the I is the rainfall intensity. Um, so then uh, this is acre inch per hour if I use a rainfall intensity of inches per hour and the area in acres. If I use if I want cubic meters per second, then I use the intensity in meters per second and the area in square meters. Okay, so these are my conditions. Okay, so I have used a coefficient of runoff for pre of 0.35 and an intensity of 2.8 inches per hour, and a post construction condition of with a runoff coefficient of 0.5 and an intensity of 3.1. So basically what you do is then say the pre-construction QP would be 0.35, 2.8 inches per hour, and it's 250 acres. Okay, so let me calculate that real quick. So, not real quick, but 0.35 times 2.8 times 250. So I have 245, and that's acre inches per hour, which is acre inch per hour is about 245 CFS. Okay, so then this is free, and then the post I have 0.5, 3.1, and 250. So 0.5 times 3.1 times 250, 387 CFS. So we have increased 387 minus 245. So 142 CFS. So by having that construction, you have increased the runoff by 142 CFS, or 142 acre inches per hour. So you have to provide that additional storage. to manage that stormwater runoff. Okay, so then the part two would be to do the same thing for El Paso. So rather than giving you that um, generic idea for that I'm using for most problems, you have to calculate for El Paso. So the easiest way is to calculate um, the time of concentration using this Excel file I gave you. Remember, it's for a 10-year. So you have 1.7 inches per hour, and here you have 1.9 inches per hour. Okay, so that is the difference, and so um, the Q equals CIA would be like before we had, I guess it was 0.35, 0.35. So now the intensity is 1.7 inches per hour. I still have the 250 acres, and the here would be CIA, and then I had 0.5, 1.9 inches per hour, and an area of 250 acres. So in this case, I have 0.35 times 1.7 times 250, 148.75 CFS, and then zero point 0.5 times 1.9 250, 237.5. So I have generated an additional 88.75 CFS. Now remember, this is inches per hour acre, or acre inch per hour as well. Acre inch per hour. Okay, so that's the solution for El Paso. Remember, there's the design standards and there's the resources. Make sure you check them, and thank you very much. Hope this has been helpful.